Okay, welcome again, everyone. So in this section, we'll actually begin talking about geometry, and we'll begin with this concept pertaining to some very important terms in geometry. Terms that happen to be undefined. And when we say undefined, we mean that they cannot be, they cannot be given a formal definition, but they can be described. Such terms can have their main features described and identified. And these terms include points, lines, and planes. Okay, so let's look at points. So a point can be described as a location or position that has no size. Okay, so what do we mean by it having no size? So let's say, if we had a number line, for example, and we picked a point, or, if we picked a point in space on a 2D coordinate plane, if we picked a point here, the point essentially denotes this position in the 2D coordinate plane, xy, right? So it would pertain to these two coordinates, right? Whether it were this small or this big, it's still a point. It has no spatial size. Okay, you can always say, well, if it's so big, it seems like it would include multiple points in it. Well, no, by definition, if it is a point, just take the center, for example, of it. Just take the center of it, and that center would refer to the position in space. As you can see, it's fairly arbitrary. I mean, the size discussion can be ongoing, but just understand that a point should not have any size. Okay, no size. It pertains to a certain location in space without size. A point can be represented by a dot, as was just mentioned, and has a name. We name points using a capital letter. For example, this is point A. Okay, the dot is point, and then the name of the point is point A. The second important term is lines. Now, a line can be described as a straight path that has no thickness. Okay, extends in two opposite directions and consists of an infinite number of points. Okay, so line AB, for example, right here. So it's a straight path, meaning it's straight. It's not curved, for example. It's not. This is not a line, right? This is some curve, and it has no thickness. What does it mean for it to have no thickness? Well, that means that it actually extends. One says it extends in two opposite directions, but the extension, though, the line extends still in a single dimension. Okay, so for example, we know we have the three dimensions, right? X, Y, and Z, right? X, Y, and Z, for example. This line can extend, for example, let's make it extend in Y, right? But it has no extent in X or Z. And what that means is that, let's think about it in terms of the point makeup of a line. So here we say a line consists of an infinite number of points. So again, since we said that points do not have size, you can't say that, it takes 30 points to make this line or it takes 100 points to make this line, because you can never determine how small or how large a point is. But if we have an infinite number of points, we are going to end up with a line. Okay, in a single dimension, we're going to have a line. But in the thickness dimension, though, which is this dimension, right, there is no thickness. Why is there no thickness? Well, because the thickness of the line is only 1 point thick, right? So the line is made of point, etc. So the thickness this way, right, is only 1 point, right? Only a single point, right? But the thickness this way is multiple points, right? Infinite points. And that's how you get a line. Okay? So again, to recap, a line consists of an infinite number of points, but it has no thickness in the thickness dimension, but it does have spatial extent in the dimension that extends in. Okay, this line above is called line AB because it's defined by these 2 points. In symbols, it is represented by AB. And there are different types of lines we'll discuss later, but just keep that in mind, okay? Let's move on to planes. A plane can be described as a flat surface that has no thickness, extends in all directions without end, and consists of an infinite number of lines. So we talked about a line consisting of an infinite number of points, right? Such that the thickness is, well, there's no thickness because it's only 1 point thick, and again, we cannot determine, we cannot, define how thick a point is, or how big or large or small a point is, okay? In the thickness dimension. But in this dimension, again, since there are infinitely many points, we do get a line. Okay, we do get something. We do get size. Okay? Now, a plane is the next level up from a line. So a point has no dimension. Okay, it has no spatial extent. A line has spatial extent in a single dimension. Okay? A plane is the next step up from a line. If you put multiple lines together, again, infinitely many lines, again, because remember, each one line has no thickness, right? So again, you can't say how many, it takes 10 lines to make up this plane. No, it doesn't. It takes, or not even 1,000, not even 10,000, not even 1,000,000 lines. It takes infinitely many lines to make up this plane, okay? Because again, each line by itself has no thickness, but if you put an infinite amount of lines stacked next to each other like this, you end up getting a plane, okay? And again, a plane extends in all directions without end. So for this plane, for example, it's really, it's even bigger than this, right? It's so big. It extends up to infinity. Because again, these lines are infinite lines, okay? Here's an example. So the plane above is called plane P. Okay? It is represented by the capital letter P. The dot is just to denote that it refers to this plane. Okay? Let's look at some exercises. Please pause the video, work on these, they're pretty straightforward, and come back for the solution. Okay, name the following points, lines, and planes. Very simple. Again, this is to get you used to the convention, because again, geometry builds up on itself. Just like algebra, but probably even more so, it is all related. So this may seem simple now, but it will build up on itself. So if you understand these basic concepts, you should do well moving forward. This is point A, right? This is line EF, right? Or it could also be written as EF, okay? Line EF. This is plane M. All right. The ideas of collinearity and coplanarity. Collinear points are points that lie on the same line. So if I had X and Y and line L, if points X and Y both lie on line L, then points X and Y are said to be collinear. Okay? So if I put another point here, for example, Z, right? Then Z is not collinear with X and Y, with neither X nor Y. Okay, because Z does not fall on the same line as X or Y. You could say, well, it doesn't fall on this same line, but, well, I can make it fall on another line. Well, of course you can. You can always draw this line, for example, in which case now x and z are collinear. Or you could have drawn this line, in which case, excuse my poor drawing skills. A ruler would have helped, but yeah, okay, there we go. So, yeah, and so now z and y are collinear on this line, right? Let's call this line m and n, okay? So L, M, N, right? So now z and y are collinear for line n, and then x and z are collinear for line m. But at this point, we only have line L. We are working with line L. So in this case, the reference line is L, and now we are testing the collinearity between these 2 points based on line L. So if they're on line L, okay, x and y, then they're collinear. Points x and y are collinear points on line L. Coplanar or coplanarity refers to points and lines on the same plane. So while collinearity defines points that fall on a single line, right? Coplanarity refers to points and lines on the same plane. So let's say we had a plane like this, plane P, and we had a point B on the plane, right? Like not above it or below it. So again, if I drew this in 3 dimensions, it would help you understand a little better, right? So this is 3 dimensions. These are more planes, right? I mean, you can always, close this shape off or extend it in space, like up and down, right? More planes, right? You get the idea, right? So 3 dimensions. So these are even more planes, right? If point B, for example, fell on this plane here, then point B is not coplanar with line AC. So line AC also falls on the plane P, okay? But if either of them fell on another plane, right, so all these are planes, full planes, that extend up or down in, the 3rd dimension. Whereas plane P has its own 2 dimensions. So there's this dimension, there's this dimension, and then there's a 3rd dimension up or down, okay? So as I said, point A in this case, or point B, sorry, happens to fall on plane P, and so does line AC. In this case, these 2 items, right, point B and line AC, are considered coplanar on plane P. Okay? Alright, and here we have more exercises. Please pause the video, work on these, and come back for the solution. Okay, use the figure to the right to answer the following. Name 2 points that are collinear. So again, we spoke about collinearity, and we said that it has to be any 2 or more points that fall on the same line, on the same existing line, not on the same hypothetical line that you can draw at any point, right? So they have to fall on an existing line. Here, what is the only existing line? Well, it's this line. What 2 points happen to fall on this existing line? Well, Q and S, right? So point Q and point S. Okay? Name 2 points that are coplanar. So this one is pretty easy also. You can take any pair of these 2 points, right? Since all of them do fall on plane R. So I could have taken V and S, or I could have taken V and Q, or I could have taken Q and S. Any of them work. Okay, so let's just say point V and point S. Okay. All right, and this is it for this concept. See you in the next video.